Okay, so picking up from where we left off last time. So we talked about vector fields, and we talked about how vector fields can represent forces and various examples. So we're going to talk now about how vector fields can represent something very, very different from forces, namely just the flow of a fluid. And again, when you look at a picture of a vector field, very often that's what you see. I see a stirred pot when I look at this picture here. Right? Okay, so there's lots of different types of fluids that flow. A couple of obvious examples here, right? The one I think is maybe a little bit sort of an eyebrow raiser, animal migration. Seems like a weird thing to think of as a fluid flow. But animals, after all, usually not fluids, right? But if you think about what a fluid really is, a fluid is made up of a bunch of particles, aren't they? Right? Water is made of a bunch of molecules. So if I were to look at a migration pattern of, locusts, something like that, right? There's bazillions of them, and they're all kind of flowing kind of generally the same direction. That's a lot like having bazillions of molecules of water that are flowing along. So really ultimately not that different. And then of course you get up to, wildebeests or something like that, and then it's a little different, but still they tend to go somewhat together, and it's a little bit coarser of a fluid perhaps, but you could still think of it as a sort of a fluid. Okay, so here's a nice calculation. This is going to segue into something important. It's going to start off as just a natural question to ask. So suppose you have a vector field representing the velocity of a fluid. Very often, this is what it means when we say that a vector field represents a fluid flow. At any given point in space, let's take the air in this room, there's a certain amount of airflow happening in here. At any given point in space, we can talk about at that point, what direction is the air flowing and how fast. And so at every point, there's a vector. That's a vector field. Okay. Supposing that I know the vector field representing the flow, and supposing further that I have a small flat area like this. Right? I could reasonably ask the question, okay, if I know the velocity of the fluid and I know the area, then how much volume per unit time of fluid, or how much fluid is flowing through this area? What's the rate that fluid is flowing through that area? And when I say rate, in this case, what I mean is volume per unit time. This is what we're going to call the flow rate. Okay, so I distinguish between, if you have a water hose and water is shooting out of the water hose, let's not conflate the velocity of the water with how many gallons per minute is coming out of the hose. Does everybody see the difference that I'm talking about there? Okay. All right, so here's how we do it. Let's talk about a small amount of time delta t, and in some small amount of time delta t, the fluid is all flowing through like this, and after some small amount of time, this is literally the fluid that has flowed through this area. It's a little parallelepiped like that, and I can write down a formula for the volume of that parallelepiped. This is an old formula from high school geometry, but it is height times area, which we already are given. Height times area. Is everybody cool with that? Okay. All right, now how am I going to compute this height? Well, gosh, so I claim that height is it's a component. Specifically, it's a component in what I'm going to call the normal direction. Let me clean up my picture. The normal direction defined by this unit vector in that points perpendicular to the A. And now real quick, this normal vector is actually going to serve two purposes. One purpose is to be literally perpendicular to my area. It's going to be a convenience in understanding how this area is oriented. But the second purpose that this normal vector serves is to define which direction I consider to be the positive direction through the surface. So there is a difference between water flowing this way through the surface versus water flowing the other way through the surface. They're intrinsically negatives of each other, right? And so if I want to know the flow rate, if the water is going back into the hose, that's different from the water coming out of the hose. So this defines what we're going to call the positive or the correct or the intended, however you want to say it, the positive direction through the area. Okay. So, so I claim that the height is just the component in that normal direction of, oh gosh, did I run out of colors? I'm going to use dark blue here. This D vector. And this D vector, I call it D because it represents displacement. Now, of course, it's the same all the way across the thing here. I'm just highlighting it in several places. This one I'm highlighting now might be the one where it's easiest to see what we're saying here. This displacement, how much the fluid, in the amount of time delta t, how much has the fluid moved? It's not going to be exactly in the direction we care about. The actual height here needs to be perpendicular. But if I take the normal component of that displacement, that'll tell me this height. All right. Good news. Components are computed by dot products. That's convenient. Now, wait a second. Dot products only because this normal vector, by assumption, is a unit normal vector. Right? Otherwise, we'd have to divide by the magnitude, and it's just a weirder formula for components. So life becomes simpler if we just agree that we're gonna define orientations by unit vectors. So that's something to keep in mind. And then dot product. All that's left to do is figure out what is this displacement vector. And this is actually not that big a deal, the displacement vector. I know the velocity of the fluid, and I want to know how much it displaces in some time delta t. That displacement is just velocity times delta t. And of course, the velocity is the field vector. So, little details going through the calculation here, but there's a nice punchline. What this computes for us is how much volume has gone through in time delta t, or you might say instead, if I were to divide by delta t, that would give me volume per unit time, take a limit, stuff like that, and out comes the answer, volume per unit time, aka flow rate, and it's just this dot product right here, F dot N times A. Everybody good? Little details there. Okay. So, so nice result. This is a pretty general question. We have a fluid flowing in an area that it's flowing through. How much stuff per unit time? Very natural question to ask. So this answer is worthy of a name. This is called flux. We use the capital Greek letter phi, not to be confused then with the lowercase that we use for the spherical coordinate. Right? So capital phi represents what we call flux. All right. Okay, by the way, we're going to do a lot of stuff with flux, very largely in chapters 6 and 7. We're just going to do a few things with it here. It's going to be one of the primary objects of study in chapter 7. Okay, so now I'm going to ask a very similar question. Very similar question. This time, instead of the vector field representing velocity, what if the vector field represents density times velocity? Now, I know that seems weird the very first time you see it, but here's an example of why I might care about such a thing. So suppose I have a door or a window or something in my house, and it's been left open, right? It happens sometimes, and I'm concerned about the rate at which, flies are coming into the house. Well, how fast the flies are moving is part of the story. If they're flying faster, more of them are going to come in per unit time. But it also matters how dense, right? And if there's only one fly per cubic yard of volume, well, they're not going to be coming in very fast, right? But if there's 500 flies per cubic yard, they're flying the same speed, well, reality is there's just a lot more flies coming into my house. Does that make sense, everybody? So density, interpreted in the general sense, maybe mass per unit volume, but maybe just count, number of flies per unit volume. However you choose to describe density, it's another factor that ought to contribute to how many flies are coming into my house. So here's the question and the answer, by the way. How would I compute not volume per unit time of fluid, but quantity per unit time of fluid? And again, appropriate to however you're thinking of density, number or mass or what have you. And it turns out the answer is, again, this exact same formula called flux. So the way you're going to prove this, and you'll notice I have a big gap down here. I want you all to fill in the blanks on this. It's a really nice exercise. What you're going to do is pretty much use this argument here. It's just that instead of computing volume in a given amount of time, you will compute mass per unit time. Mass, of course, is volume times density. And then all of this kind of proceeds the same. This factor of density would just kind of come along for the ride, right? And then I'm going to let you all think it through here, but where does that density factor go at the very end, with the punchline being that, again, flux. Same formula, flux, will be computing mass per unit time. So, again, I think this is a healthy exercise. I want you all to think it through on your own. If you get stuck, as usual, right, if you get stuck on any of these suggested exercises, come to office hours. I'll be very happy to help you think it through. Of course, you also have other instructor office hours. You also have the help room. You also have classmates. But I think this is a nice exercise to think through. Okay. All right. And going over to the next page now, this is the interpretation that we're going to take of flux. We're going to consider that vector fields represent density times velocity. We're going to be thinking of quantity per unit time of fluid going through our surface. And it's going to be understood to be computed with this formula here called flux. Okay, so with that in mind, I want to consider a harder scenario, and that is where you have an uglier kind of fluid. Let me first talk about what's been convenient about the fluids we've been talking about. We've been talking about water, made up of a bunch of particles, sure, but as the water flows, right, all the particles of water are kind of going kind of with each other. Water never kind of passes through itself, or you never have water simultaneously going sort of all different directions. It gets in its own way, and they all have to kind of go in some sense together. Likewise, with like a flock of birds, right? If you watch a flock of birds, they might kind of change their patterns and everything, but they all kind of generally go with each other. They don't cross each other's paths. It'd be all sorts of mid-air collisions, and that just wouldn't work, right? So, sadly, not all fluids are like this. My favorite example, photons generated by light bulbs. So, for example, here's a light bulb, and light bulbs shoot out a fluid called photons. Particles, of course, right? But they can think of a bunch of small particles as a fluid. So there's a light bulb shooting out photons in all directions, and among other things, it's going to have, way over here at a point like that, it's going to be shooting out. It's going to, there will be photons at this point that are going that way because they came from that light bulb. But there's also this light bulb here shooting out photons every which way, right? And at this same purple point, there will also be some light going that way. So this is exactly what we were saying. You probably never see this in a flock of birds, right? Birds kind of at any given, wherever you're looking, all the birds nearby there are kind of all going the same way so they don't cram into each other. Photons, I don't know how much y'all know about physics, but photons can just pass right through each other. There's really no problem. So at a point like this, the ugly issue we have to deal with is I can't talk about the velocity at this point. Because there's some of the photons have this velocity, some of them have that velocity. Which one? Or do I add them or something? I mean, it's really not clear what I should do to describe this. Is everybody with me? Okay. All right. So what we're going to do is change our point of view on things. And I'm going to kind of turn this equation around backwards. So this is the equation from the previous page, that quantity per unit time computed by Flux. And previously, we've thought of it as, suppose I know the vector field, and I want to compute the flow rate. This formula allows me to do it. Now we're going to turn that around. And I'm going to say, let's suppose I know flow rates. However I might know flow rates. Maybe it's empirical. Maybe I'm just literally measuring. Or maybe I have some clever argument that I can make, and we're going to do that in the next example in a couple of minutes here. But one way or another, suppose I know all of my flow rates through whatever surface. Can I kind of work backwards, reverse engineer, find a vector field that's consistent with all of those flow rates by way of this formula? Is that cool? So we're going to define, in other words, in a weird fluid, like with the photon example. And by the way, in this room, the photons are crossing through each other, all going every which way, because we have a ton of light sources in this room, right? So what vector field would I use to represent the flow of photons in this room? Well, whatever vector field makes this formula work for all of the photon flow rates that I can compute through various surfaces. Okay, so let me show you an example of how this works in practice. By the way, this is a tricky example. There's a lot of good ideas in here, though, that I want to make sure that y'all are exposed to. Some of these ideas are going to come up significantly when we get into chapters 6 and 7. So think of this as kind of a segue kind of example. So we have a uniform ball of glowing gas here. And exactly what is this glowing gas? I like to think of it as being like neon or something, like a neon sign, that kind of thing. So uniform ball of glowing gas. It occurs to me that the sun is also somewhat uniform ball of somewhat glowing gas, right? So you can think of that if you'd prefer, but I find neon a little bit more relatable. So, okay. What is the vector field representing the photon flow here? And it's a preposterously difficult question. Like at that point, well, there's some glowing gas over here that's making photons that go that way. There's some glowing gas over here that's making photons that go that way. And there's some glowing gas over here that's making the photons go that way. Which of these velocity vectors do I pick? I don't know. It's too complicated. It's too weird. Photons are flying all around every which way. Now, okay. So, the field itself, hard to talk about. What is surprising, importantly surprising, is that fluxes are actually not that bad. We can describe the fluxes pretty easily. The flow rates, I should say. So let's think about, for example, this sphere. And I want to talk about the flow rate of photons through this sphere, and by the way, oriented outward arbitrarily. I want to think of that as being the positive direction. So photons that are going in to the sphere, I want to consider that to be negative flow. Okay, well, here's some really good news. All of this gas, like let's say for example over here, I claim I can just ignore it. Interested as I am only in this surface, what contribution does this particle of glowing gas make to the flow through that surface? Answer none, because every photon that flows into this surface also flows out of this surface. Exactly the same amount. So, poof, cancel, nothing. Does that make sense? It's a really cool observation. But every time a photon has flowed out of this sphere, it must have also come in to this sphere. So the outward flow is equal to the inward flow. The total flow is therefore 0, as coming from these particles. So that really simplifies things quite a bit. What that means then is I only have to consider the glowing gas on the inside of this sphere. And now let's think about the glowing gas on the inside. There's a certain amount of particles in there, and they're glowing. They're shooting out photons. Which of the photons that originate inside of the sphere pass outward through the sphere? All of them. It's as simple as that. All of them, right? So I claim that what that means is that this flow rate outward is just going to be proportional to the volume of that sphere. It's as simple as that. Whatever the volume is, however much volume you got, I mean, yeah, there's some proportionality constants. Let's not worry about the proportionality constants. But however much volume you got, the more volume you got, the more gas you got. The more gas, the more photons. The more photons, the more flow rate. It's all just directly proportional. What do you think? And again, important fact here, I am lumping together, there's a bunch of details in this K that are not our problem. Right? So how dense is this gas? How much energy per unit volume is being emanated by the gas? How much energy is there in a photon? And how much of, that constants, not our problem. Okay, so, again, very, very difficult to talk about the field, but the flow rate is easy. It's just proportional to volume. Okay, now with that observed, that's one of that's our primary observation, but there's a couple other observations I need to make in order to finish this calculation. The next observation I'm going to make is that the vector field representing the flow should be radial. This is just an intuitive appeal. I don't want to spend a lot of time on this, but at a given point, wherever I might happen to be, if that's the radial line from the center at that point, which direction is the vector field going to point? Well, everything in sight is symmetric. It's a uniform ball. The ball, being a perfect ball, is perfectly symmetric. And so I claim that the vector field there's just no way that the vector field could be like that. Right? Off axis. If it were off axis, which direction off axis would it go? Right? There's no asymmetry to make it possible for there to be an asymmetry in the vector field. Again, intuitive appeal. I hope that's satisfying. Okay, so it's radial. So we're going to look at now a centered sphere, centered at the origin, in other words, centered at the center of the ball. And the vector field is going to, let me switch to there we go. The vector field is going to be radially outward, uniformly radially outward like that. Here's the other thing, though. Let's talk about the normal vector. Keep in mind we're looking at a sphere here centered at the origin. The normal vector, its job is to be perpendicular to the surface. Again, intuitive appeal. Perpendicular to a sphere centered at the origin is also radial. It's also pointing straight outward. So, while we're at it, then I'm going to go ahead and observe that this dot product we will eventually be interested in, F dot n. Well, the vector field is radial. The unit normal vectors that I'm dotting with, also radial. So this is a dot product of two vectors pointing in exactly the same direction. And so that means I just get the product of the magnitudes. Oh, wait, this one's a unit vector. And so the product of the magnitudes, it's just the magnitude of the vector field. That's it. Is that cool? All right. And now we're ready to finish it up. So here's the formula that we argued a few minutes ago. Flow rate only depends on volume and constants that we're not going to worry about. That formula I'm going to rewrite as this, but it's going to take me a minute to do it, so bear with me. Step by step, here it goes. This volume is the volume of a sphere, and that's an old formula from high school. Hope everybody remembers that. Our definition of the vector field is that Flux needs to compute flow rates. So this has got to be true, that I have in blue here. We just got through computing F dot n. It's the magnitude of F. And another old fact from high school, area is 4 pi r squared. That's the area of the sphere. So, the purple formula, the top purple formula is turned into the bottom purple formula. And it's practically over at this point, as it turns out. I can solve for the magnitude of F. I know that F is radial. And in fact, there is only one vector field that is pointing radially outward from the origin everywhere, and whose magnitude is exactly this constant times distance. And that's this vector field right here. So there you go. We have a vector field now that represents, even though there's glowing gas everywhere, the photons are going every which way, nevertheless, this vector field computes the flow rates for us. Yes? I kind of worked backwards. If I were to take this vector field and compute its magnitude, the magnitude would be that. Because the magnitude, so keep in mind, arguably I should have used rho instead of r here, but that's just distance from the origin. I used r here because I was thinking of it as a radius of a sphere. Arguably it should be rho. But the point is the magnitude of x is distance from the origin. So that's what happened there. Is that satisfying? Okay, cool. All right. So like I say, it's kind of a hard example, but I think this is a good exercise. Several of the arguments that I've made here are things that we're going to use in Chapter 7. Okay. All right. Last thing I'm going to say about this section is to define something called a flow line. This is a relatively believable idea, I think. Let me go back to this vector field. Imagine this is I like to think of this as a stirred pot, right? And so there's a pot of water, and I stirred it like that, and it's doing like this. So imagine now that you had a piece of lettuce that you toss into your pot, right? And it's, I'll use green for lettuce. There it is. There's that piece of lettuce. What's the piece of lettuce going to do? Well, it's going to go exactly where the flow of water tells it to go, right? So the water is going to start by going that way. But then the further you go up, the more the vector field itself kind of turns. And I'm going to appeal to your geometric intuition. If you stir a pot and you drop a piece of lettuce on the surface, it's going to go around in a kind of a circular pattern. Yes?
Are vector fields related to differential equations?
Yeah, we're about to develop a differential equation. That's right. We're in the process. Yeah, totally. Yeah, but give me a minute to get there. Okay, so this is called a flow line. This curve representing the path followed by a particle that is just flowing along with the fluid. That's called a flow line for the vector field. And here's how I can write that down. Looking at this kind of annotations down here. The velocity of the particle, if we've got a particle that's following the fluid, the velocity of the particle has to equal to the velocity of the fluid. But specifically, the velocity of the particle is equal to the velocity of the fluid wherever the particle is, right? So it's where the particle is, it's that fluid's velocity that tells the particle what direction it needs to be going, right? So if I stirred the pot and I drop a piece of lettuce, the lettuce is here. I don't really care about what the velocity of the water is way over here, right? It's where I actually am. It's the velocity of the water at that point that tells me which direction the little piece of lettuce is going to go. Velocity of the particle, derivative of the parametric curve gives you the velocity of the particle, equals the velocity of the fluid, and specifically the velocity of the fluid wherever the particle actually is at that moment. And then don't forget, the velocity of the fluid is how we're thinking of the vector field. So altogether, I have this equation right there. And this is what we call a system of differential equations. We do not currently have the tools in this class to solve a system of differential equations. You will in Math 353. That's one of the things that they'll talk about. There's some cool ideas in there. Okay, I'm just going to show you an example where we're not going to solve the differential equation, but I'm going to give you a solution and we're going to confirm that it does actually fit. So here we go. Here's the stirred pot, vector field, right? And I claim that, you know what? I did that in the wrong color. Water is blue. There's the stirred pot. I claim that the little chunk of lettuce is going to follow a path kind of like this. And the way you're going to confirm it is you're going to take this formula, you're going to plug it in there, you're going to plug it in there, meaning that you're going to take the derivative to compute the velocity of the lettuce. You're going to plug into the vector field to compute the velocity of the water where the lettuce is. And then you're just going to ask, are these equal to each other? And by the way, the answer is yes. And that makes this a flow line of that vector field. Now, details, again, you'll notice I didn't work them out. This is a good exercise. Please do these details. Plug in that into the system of differential equations, compute it out, take the appropriate derivatives, compute it out, and confirm that does work. Office hours if you have any questions, of course. Okay. There we go. All right. So last thing I'm going to say real quick is just a heads up. While I've given you two different kind of physical metaphors for vector fields, we've talked about vector fields as representing forces, gravitational forces, electric forces, that kind of thing. We've also talked about vector fields as representing flows of fluids. It's not just that these are two examples of vector fields in use. It's that these are critical examples, both of them. So you can't choose between these and think, I don't know, for my mind somehow this one here just makes more sense intuitively. I'm going to think of all vector fields as representing fluid flows. Now, you can't really do that. There are some things that we're going to do with vector fields that require thinking of the vector fields from the point of view of forces. That's going to happen where you just have to think about the vector field as forces. Likewise, there will be some things we're going to do with vector fields that will require that you think of them as representing the flow of a fluid. So, take whatever time is necessary so that you become comfortable thinking about both of these. Right? And furthermore, be sure when you're making some interpretation about vector fields that you're clear about which one of these are you actually thinking about at any given point in time. There are some pieces of intuition about vector fields from the point of view of forces that will confuse you if you then try to apply that to fluids. Right? So heads up that we have two important ways of thinking about vector fields. Okay. And now I move on to section 3.4. So this is a weird section, and we're going to cover this pretty quickly. A lot of this is just kind of foreshadowing. This is just introducing some ideas that are going to be a big deal later on, mostly chapters 6 and 7, mostly chapter 7 in particular. And there's a lot of really beautiful ideas in chapter 6 and 7, but there are also a lot. There's a lot of ideas in chapter 6 and 7, and so we're going to try to present some of the pictures and some of the intuitions now, just so you can kind of be digesting and chewing on it. And then when we get to chapter 6 and 7, so much else will be going on. We don't want these pictures to kind of come out of nowhere for you. Okay, all right. So first of all, let's talk about the gradient. Here's the formula for gradient. Old news, y'all remember this. And I want to think of this a little bit differently. Think of the gradient as being now this. That's a little bit weird, I'll grant you. But we've got a scalar function f. And what we're doing to that scalar function f is, well, we are going to make a vector out of the various partials of it. That's just a notational choice. If you want to, you can think of this as that it kind of looks like a scalar being multiplied by a vector. And when, of course, you have a scalar times a vector, the scalar gets multiplied by all of the entries in the vector. So either way you like, whatever. But this is a standard sort of a notational alternative for gradient. So once we've done that, then we can distinguish between the function that I'm taking the gradient of versus this operator, this vector of partials. This operator that I'm applying to f to get the gradient. This is called the del operator. Now I emphasize, del is not the same as gradient. Del is just the operator. Gradient means the result of applying the del operator to a function. So del of a function is the gradient. Does that make sense? Just a little terminology and notation. Okay. All right. So coming out of nowhere, and I'm not going to be able to justify this here, but the justifications are going to come later. We're going to define something called the divergence of a vector field. And it's, for the moment, it's a formula and a piece of notation, and I'm going to make an assertion about what it looks like geometrically, and that's all we're going to do. I'm just going to make some assertions, draw some pictures, and then we're going to move along. Okay, so here it is. If you take the del operator, if you take a vector field, f, and if you do a dot product, that's very important that this is a dot, del dot vector field. And again, sort of interpreting, the kind of the usual way. What do we do with a dot product? Well, the first coordinate and the first coordinate, and then the second coordinate to the second coordinate, third coordinate to the third coordinate, right? So, well, here you go. Del, one coordinate at a time being applied to f. One coordinate at a time. Wouldn't this be a kind of a reasonable interpretation of what we ought to mean by del dot f? Is that cool? I guess it's just a notational kind of convenience. Okay. All right, so now I've written down some arbitrary stuff. This doesn't prove anything, of course. So I'm just going to make an assertion yet. Again, with this apology, we don't have the tools yet for me to be able to make sense out of this. Right? And we will. But for the moment, I'm just going to make an assertion that comes out of nowhere. My assertion is that divergence, this formula, what that represents is it represents how much a fluid is flowing generally away from a given vicinity wherever you're calculating it. I know it sounds weird. Let me show you an example. Okay, here's a vector field. Y'all may recognize this vector field. The field vector is the same as the position vector for where you're evaluating it. Right, and we talked about an example. We talked about a two-dimensional version of this previously, but the point is all the vectors point directly away from the origin, and with magnitude equal to the distance from the origin. So you get something kind of like this. Is everybody okay with this claim? Okay. All right. Okay, so that's what this looks like. Let's compute the divergence. Now this is just a formula. So again, del. Here's the del operator. F has coordinates x, y, z. Right, so literally computing divergence per the formula that we just scrolled past, and the pretty easy algebra, and the answer turns out to be 3. So what does this 3 mean? More to the point, what does the fact that this is positive, this divergence is positive, what is that? How does that represent on the picture? Well, this says that there is a positive amount of outward flow away from where I've computed this. And notice you can see that kind of in the vector field. Right? The vector field, if there were a fluid here, this fluid is emanating out away from the origin. Is that cool? Okay. And I think you could probably imagine that if I were to toss a minus sign into all of these coordinates, let's see if I can squeeze this in here. If I put a minus sign in front of all of those, thus giving me the exact negative vector field, that would have all of these arrows pointing inward. Right, all inward, and the divergence, if you were to compute it, well, it would be negative. And so negative means fluid flowing inward toward a point, that being the negative of outward from a point. Yeah? All right? Okay. So as claimed, I mean, this is just an example, but divergence being positive suggests an generally outward flow away from where we're computing it. Now, let's ask the question, what does this look like physically? What does this represent? What's actually happening here? Like, what do you see in this picture? And there's a couple things I could see. On the one hand, I could imagine that maybe there's a tree right there, and there was a bunch of birds in that tree, and then somebody came by and scared them, and they all got up and started flying away, and this is the flow of the birds away from that tree, right? And if that's the case, then let's think about how many birds there are in the vicinity of the tree, and how is that changing as they fly away? Well, a positive divergence here, right? Outward flow, birds leaving, I'm going to have less birds over time, right? As they leave, there's less of them remaining there. So you could think of this as indicative of, whatever the nature of the fluid is, maybe the fluid is, because it's leaving, the fluid is becoming less dense where it was. That's one interpretation. Now, here's a totally different interpretation. Let's suppose it's got nothing to do with birds. Suppose this is where a light bulb is. Right? This is a light bulb. Are we losing photons? Are we having a less? Do light bulbs do they have like a finite number of photons in them, and as they flow out, then you lose photons, and eventually you run out of photons? No, not at all. Light bulbs they generate photons. Right? So, in this metaphor, we're not losing photons. Photons are being created. at that point. So that's a different interpretation of positive divergence. Right? A different physical reality, and you have to make a different sort of sense out of what that positive divergence means. So you always have to kind of interpret, and by the way, it could be worse than this. It could be that it's actually a combination of both of these. That can happen too, and we don't want to get into those weeds. But yeah, question.
So, are we saying like birds are being created?
No, yeah, no, exactly. It's a great question. But no, so different interpretations for different metaphors, right? Birds are, of course, obviously not going to be just spontaneously generated. Someone went over and said "boo." That doesn't create birds, right? That gets us back to the decreasing density. That there were a lot of birds here, and then they started to fly away. And as they fly away, the more that they fly away, the more that this happens. In other words, the less birds there are.
So the meaning of the sign of the divergence depends on content.
It depends on it depends on the physical reality that you're describing. And the thing is, there's just different kinds of fluids. Birds are not like photons, right? And so you have to interpret differently accordingly. We do generate photons. We literally create photons. We don't create birds. And so, yeah, just different interpretation because of the different fluid, the different, reality that we're describing. Okay. All right. Here's an example where the divergence is 0. This one's, I think, pretty believable. Vector field looks like this. Again, a good exercise to think through, make sure you're comfortable with this being what that vector field looks like. I want to make sure you can do that. We compute the divergence. We get 0. Easy arithmetic or algebra there to compute that divergence. What does that mean? Well, that means that, for example, if you're looking at, let's say this vicinity right here, divergence being 0 means that the fluid, it's just not in any sense emanating from that point. There is some fluid coming outward from that point, sure. But there's just as much fluid going inward toward that point. So it's kind of a wash. And so, for example, if there were maybe this is people walking in a crowded boardwalk or something, right? Then there's a lot of people walking fast that direction, and down here there's people walking fast in the other direction, and kind of in between they slow down, and there's crossing through and other little things like that. But generally speaking, if this is the path, this point here, a lot of people walking through that point, but this is not a source of people. Right? That makes sense? There's, the people walking out of it, because they walked into it, that's where they came from. So it's just, right. Okay. All right. Let's see here. I got a minute and a half left. Another arbitrary definition I'm going to make, seemingly arbitrary. It's actually not at all arbitrary, but it's going to look arbitrary. Another very natural quantity that ends up being something we can define with the del operator is called curl. It is computed as del, which you see right here, cross our vector field F, which you see right here, and of course cross product. Right? We know how to do cross product. You put the standard basis vectors across the top. You make a matrix in this way. You take the determinant. Again, symbolic determinant. It's not an actual determinant. Del is not an actual vector. This is all symbolic, and we're allowing interpreting loosely. Okay. So again, I can't give you any context or motivation for why what I'm about to claim is true, but here's what curl represents. Curl, this thing here, represents, in its own way, it represents a sort of a circulation, like a rotation, like this kind of thing, like a tornado, a whirlpool of water, when the fluid is kind of rotating around itself, something kind of like that. And specifically, the curl tells you by its magnitude, it tells you how much. Is this a violent whirlpool, or is this just a gentle kind of slow rotation? And by its axis, it tells you what the fluid is rotating around. And quick example, y'all will recall the stirred pot. There's my stirred pot vector field made three-dimensional. And so, imagine an entire pot where the fluid is all kind of flowing around like this. You can compute the curl per the formula above. You get 002, which is like this. And sure enough, right, this vector, the curl vector that we've computed, the fluid is flowing around that. Right? And furthermore, right-hand rule consistent. Right? The vector field is if I point my thumb in the direction of the curl vector, the vector field is flowing in the same direction that the fingers of my right hand suggest. So again, we don't have the tools to be able to give a motivation for this, but this is what curl does. And we'll have to draw the line right there. We'll pick up here on Wednesday. See y'all later. Stick around if I didn't mark you down for attendance, and y'all have a good day.